Expert predictions on Mars travel, the future of propulsion technology by 2029. Date, January 25, 2025. Overview. By 2029, around 60% of space industry experts predict that advancements in propulsion technology will enable a 25% reduction in travel time to Mars, making manned missions increasingly feasible. Central to these advancements are nuclear propulsion technologies and the incorporation of artificial intelligence (AI) into space exploration, which promise to reshape the landscape of interplanetary travel. Key technologies and developments. 1. Nuclear Thermal Propulsion (NTP). NTP has emerged as a groundbreaking method to shorten travel time to Mars. Current chemical propulsion systems typically require a 6-month journey. However, NTP could reduce this to approximately 45 days. NASA's Marshall Space Flight Center has made substantial progress with new reactor fuels developed by General Atomics Electromagnetic Systems (GEMS) capable of withstanding extreme temperatures up to 600 Kelvin. This leap not only enhances mission feasibility but also minimizes astronauts' exposure to harmful cosmic radiation, a significant concern for long-duration missions. 2. Nuclear Electric Propulsion (NEP). NEP utilizes a nuclear reactor to generate electricity, which is then used to accelerate gaseous propellants. NASA's Modular Assembled Radiators for Nuclear Electric Propulsion Vehicles (MARVL) project exemplifies efforts to simplify the assembly of these systems in space, allowing for larger and more efficient designs. This modular approach could facilitate quicker deployment of propulsion systems in orbit, enhancing mission flexibility. 3. Artificial intelligence in space exploration. AI is increasingly integrated into managing navigation system maintenance and emergency protocols during deep space missions. This technology not only enhances mission reliability but also alleviates cognitive burdens on astronauts, allowing them to focus on more critical tasks. Common themes among experts. Across various sources, there is a shared belief in the transformative potential of nuclear propulsion technologies for manned missions to Mars. Both NTP and NEP are viewed as critical to reducing travel times and enhancing crew safety. Furthermore, experts agree that these advancements could lead to more frequent and flexible mission schedules, ushering in a new era of interplanetary exploration. Diverging perspectives. While there is consensus on the importance of propulsion advancements, different sources emphasize various aspects. One source focuses on the engineering challenges and innovative solutions for in-space assembly of nuclear propulsion systems. Another discusses the societal and economic implications of Mars missions, highlighting potential international collaboration and the growth of the space economy. A third source offers a technical analysis of fuel durability for NTP and its significance for future missions, contrasting with broader societal themes from other sources. Timeline of events. 2025, significant advancements in NTP and NEP technologies indicate the plausibility of manned Mars missions within the next decade. 2029, experts predict that these technologies will have matured enough to achieve a 25% reduction in travel time to Mars, making human exploration increasingly viable. Implications beyond space exploration. The advancements in propulsion technology are not just confined to space travel. They hold profound implications for various sectors. Societal impact. The push toward Mars may inspire a new generation to pursue careers in STEM fields, fostering a sense of global unity as nations collaborate on shared objectives. Economic opportunities. The burgeoning space industry promises new job creation and market opportunities, potentially mirroring historical space races of the past. Environmental considerations. As nuclear technology is explored for space travel, it may also lead to innovations in clean energy on Earth. Addressing pressing environmental challenges. Conclusion. The convergence of nuclear propulsion technologies and artificial intelligence is poised to redefine the timeline and feasibility of human exploration of Mars. As these technologies continue to develop, they promise not only to facilitate interplanetary travel but also to inspire global collaboration and innovation in the aerospace sector. The next decade holds exciting potential for turning the dream of manned missions to Mars into a tangible reality, marking a significant milestone in humanity's journey into the cosmos. The content presents a forward-looking analysis of the advancements in propulsion technology and their implications for manned missions to Mars by 2029. While the majority of the information aligns with common understanding, there are counterintuitive aspects that challenge conventional beliefs about space travel. 1. Reduction in travel time. The prediction that advancements in propulsion technology, particularly nuclear thermal propulsion (NTP), could reduce travel time to Mars by 25%, potentially down to 45 days, is counterintuitive when considering the historical reliance on chemical rockets that take about 6 months to reach the planet. This significant reduction in travel time is not just a matter of engineering efficiency, it fundamentally changes the safety and feasibility calculations for human space travel. The implication is that the urgency of long-duration exposure to cosmic radiation and other hazards can be mitigated, which is often underestimated in discussions about space mission planning. 2. Safety through speed. There is a prevailing belief that longer missions inherently mean greater risk due to prolonged exposure to hazards such as radiation and microgravity effects. However, the advancements in NTP suggest that by decreasing travel time, missions can actually become safer for astronauts. Contrary to the traditional view that longer missions are necessarily more dangerous. This shift in perspective emphasizes the importance of propulsion technology in enhancing astronaut safety, a factor that is often overshadowed by concerns about the technical challenges of nuclear systems. 3. AI's role in reducing cognitive load. The integration of artificial intelligence (AI) in space missions is seen primarily as a tool for efficiency. However, the content highlights a counterintuitive aspect: AI's role in reducing the cognitive burden on astronauts. This suggests that while technology is often viewed as a means to increase control and oversight, it can also enhance human performance by offloading complex navigation and system maintenance tasks, thus mitigating human error. This perspective challenges the notion that human oversight is always superior to automated systems, particularly in high-stress environments like space. For economic growth from space exploration, the notion that space exploration could lead to economic growth and the creation of new markets is not new, but the link between advancements in nuclear propulsion and environmental considerations presents a counterintuitive twist. The expectation that technologies developed for deep space travel might lead to cleaner energy solutions on Earth is a surprising intersection of space exploration and environmental sustainability. It challenges the typical view that space technology is primarily an investment in exploration rather than a potential driver for ecological innovation. 5. International collaboration as an outcome. While the drive to establish a human presence on Mars is often framed as a competitive race between nations and private entities, the content suggests that this endeavor could foster international collaboration instead. The belief that competition would dominate the narrative of space exploration is countered by the idea that shared goals in space could unify global efforts, leading to a new era of cooperative exploration. This perspective shifts the focus from rivalry to partnership, suggesting that humanity's reach into space may depend on collective action rather than individual nationalistic pursuits. 6. Public perception of nuclear technology. There is a widespread fear and skepticism surrounding the use of nuclear technology, particularly in the context of space exploration. However, the advancements in NTP and other nuclear propulsion technologies may lead to a re-evaluation of public perception. As these technologies are framed within the context of safety and necessity for successful Mars missions, there could be a gradual shift toward acceptance. This counterintuitive outcome suggests that public support for nuclear initiatives could grow as awareness of their benefits in space exploration becomes more pronounced. 7. Market dynamics and space economy. The discussion around the burgeoning space economy often focuses on private sector investments and the commercialization of space. However, the text posits that advancements in propulsion technology could lead to an unexpected acceleration in job creation and innovation within the aerospace sector. This perspective counters the typical narrative that space exploration is primarily a governmental endeavor, suggesting that the private sector's role could redefine the landscape of space exploration and open new avenues for economic development that were previously unforeseen. In summary, the content reveals several counterintuitive insights about the future of space exploration, particularly regarding the impact of advanced propulsion technologies on safety, international collaboration, public perception, and economic implications. These insights challenge traditional beliefs and highlight the transformative potential of nuclear propulsion and AI in making human missions to Mars not only feasible but also safe and economically viable. The report on advancements in propulsion technology geared towards human missions to Mars is filled with vital insights that many might overlook. While most attention tends to focus on the promising aspects of nuclear propulsion and artificial intelligence, several nuanced elements within the report deserve closer examination. 1. The role of in-space assembly technologies. Overlooked content. The specifics about the modular assembled radiators for nuclear electric propulsion vehicles MARVL project, which aims to facilitate in-space assembly of propulsion systems. Significance: the ability to assemble complex systems in space could revolutionize the design and implementation of spacecraft. Traditional rocket designs often impose severe constraints on what can be launched due to size and weight limitations. By enabling modular assembly, engineers can create larger, more capable systems tailored for specific missions. This flexibility could lead to more innovative spacecraft designs that are better equipped for deep space travel, potentially mitigating risks associated with transporting large monolithic structures through Earth's atmosphere. 2. Safety and risk management considerations. Overlooked content. The report mentions safety concerns associated with nuclear technologies but does not delve deeply into the implications of these challenges. Significance: addressing safety concerns is paramount, especially when dealing with nuclear propulsion systems. The successful implementation of nuclear thermal propulsion (NTP) technology hinges not just on technical feasibility but also on public acceptance and regulatory frameworks. The historical stigma surrounding nuclear energy could pose significant barriers. Outlining actionable strategies for risk management and societal engagement is crucial for fostering trust and support for such missions. Understanding these dynamics could also influence funding and political support. 3. Economic implications and the future of space industry. Overlooked content. The broader economic ramifications of advancements in propulsion technology, especially with regard to potential job creation and market emergence. Significance: the space industry is on the cusp of exponential growth. The report hints at the burgeoning space economy but could further elaborate on the economic models that might emerge alongside these technological advancements. For instance, a reduction in travel time not only translates to feasible manned missions but also opens up commercial opportunities such as space tourism and off-Earth resource extraction. The anticipated competition among private companies and public agencies could lead to significant job creation and innovations that spill over into other sectors affecting economies globally. 4. International collaboration and geopolitical dynamics. Overlooked content. The potential for international collaboration in space missions is noted but not fully explored. Significance: as nations look towards Mars, the geopolitical landscape may shift dramatically. Collaborative efforts in space exploration can foster better international relations and shared technological advancements. Understanding the dynamics of international partnerships could lead to more cohesive global policies regarding space exploration, resource utilization, and ethical considerations surrounding extraterrestrial life. The role of organizations like the United Nations in regulating and facilitating these partnerships could be pivotal. 5. Long-term sustainability and environmental considerations. Overlooked content. The report mentions environmental concerns related to nuclear energy but doesn't stress the potential for these technologies to inspire sustainable practices on Earth. Significance: the advancements in nuclear propulsion could have profound implications for energy systems back on Earth. As the technology matures, we might witness breakthroughs that enhance nuclear safety and sustainability, promoting cleaner energy alternatives. The lessons learned from developing reliable nuclear systems for space travel could lead to innovations that address current energy crises, thereby aligning space exploration with sustainability goals. 6. The psychological and social dimensions of manned missions. Overlooked content: the report primarily focuses on technical and economic aspects, neglecting the psychological impacts on astronauts and the societal implications of human presence on Mars. Significance: the psychological well-being of astronauts during long-duration missions is critical. Understanding the social dynamics and mental health implications of crew interactions during extended space travel can inform mission designs and support systems. Furthermore, establishing a human presence on Mars raises profound questions about ethics, identity, and humanity's future. These discussions could reshape societal perspectives on space exploration and our responsibilities as stewards of both Earth and other planets. Conclusion: the advancements in propulsion technology, particularly nuclear thermal propulsion and artificial intelligence, herald a transformative era in space exploration. However, the broader implications, ranging from in-space assembly technologies to economic growth, international collaboration, and sustainability, are critical elements that require attention. By addressing these overlooked aspects, stakeholders can better prepare for the challenges and opportunities that lie ahead in humanity's journey to Mars and beyond. Emphasizing these dimensions not only enhances the feasibility of missions but also fosters a holistic approach to interplanetary exploration that considers technical, societal, and ethical factors. 1. Advancements in propulsion technology. The development of nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP) stands as a cornerstone of future manned missions to Mars. NTP could reduce travel time from approximately 6 months to as little as 45 days, significantly minimizing astronauts' exposure to cosmic radiation and other hazards associated with long-duration space travel. NEP offers an innovative approach to propulsion by generating electricity through nuclear reactors, allowing for more efficient thrust and enabling the modular assembly of propulsion systems in orbit. This technological leap not only enhances mission feasibility but also opens the door for more flexible and frequent mission schedules. 2. Role of artificial intelligence. The integration of artificial intelligence (AI) into space exploration is revolutionizing mission management. AI systems can autonomously handle navigation, maintenance, and emergency scenarios, which alleviates the cognitive burden on astronauts and enhances overall mission reliability. This advancement is crucial for deep space missions where real-time human intervention may not be feasible due to communication delays. The use of AI thereby increases operational efficiency and safety, making it an indispensable tool in the pursuit of Mars exploration. 3. Societal and economic implications. The push towards Mars is not just a scientific endeavor but a catalyst for broader societal and economic changes. The potential for international collaboration in space exploration fosters a sense of global unity and inspires future generations to pursue careers in science, technology, engineering, and mathematics (STEM). Economically, the burgeoning space industry is likely to create new job opportunities and stimulate technological innovation reminiscent of the late 20th century space race. However, this growth also brings forth challenges such as equitable wealth distribution, commercialization of space, and the governance of extraterrestrial territories. 4. Environmental considerations and future trends. Advancements in nuclear propulsion technologies prompt a re-evaluation of energy sources and their environmental impact. As nations pursue interplanetary exploration, there is a growing emphasis on sustainable practices and the potential for nuclear technologies to contribute to cleaner energy solutions on Earth. Future trends suggest increased collaboration among nations and private enterprises driving innovation in sustainable habitats and life support systems for Mars. The anticipated transformation of humanity into a multi-planetary species may lead to significant advancements in technology and infrastructure, ultimately addressing pressing global issues such as resource scarcity and environmental degradation. 1. The Apollo Program 1961–1972. The Apollo program was a series of space missions conducted by NASA aimed at landing humans on the Moon and bringing them safely back to Earth. The most notable mission, Apollo 11, accomplished this goal in July 1969, marking a significant leap in human space exploration. The program showcased advancements in rocketry, navigation, and life support systems, ultimately leading to a new era of space travel. The Apollo missions highlighted the importance of international collaboration and technological innovation, similar to the current focus on reducing travel times to Mars through advanced propulsion technologies. 2. The Space Shuttle Program 1981–2011. NASA's Space Shuttle program was instrumental in expanding human presence in low Earth orbit and served as a platform for numerous scientific experiments, satellite deployments, and construction of the International Space Station (ISS). The program utilized reusable spacecraft, which significantly cut costs and increased the frequency of missions. The technological advancements made during the shuttle era laid the groundwork for future exploration missions, including those to Mars. The challenges of long-duration spaceflight and safe return of astronauts were central themes in both the shuttle program and current Mars mission planning. 3. The Voyager missions 1977–present. The Voyager program, consisting of Voyager 1 and Voyager 2 spacecraft, was launched to explore the outer planets of our solar system. These missions provided humanity with unprecedented data about Jupiter, Saturn, Uranus, and Neptune, as well as their moons and rings. The technological innovations in propulsion and communication systems developed for Voyager have had lasting impacts on space exploration. The program exemplifies how advancements in technology can expand our understanding of the solar system, paralleling the current advancements in nuclear propulsion and AI aimed at facilitating human travel to Mars. By 2029, space industry experts predict transformative advancements in propulsion technology, particularly nuclear thermal propulsion (NTP) and nuclear electric propulsion (NEP), will significantly enhance the feasibility of manned missions to Mars. Approximately 60% of these experts anticipate that such advancements could reduce travel time to the red planet by 25%, making missions more practical and frequent. Key technologies and developments. 1. Nuclear Thermal Propulsion (NTP). NTP utilizes a nuclear reactor to heat a liquid propellant, potentially decreasing travel time to Mars from approximately 6 months to as little as 45 days. NASA's recent developments in reactor fuel capable of withstanding temperatures up to 2600 Kelvin represent a significant leap forward. This technology not only improves mission timelines but also mitigates astronauts' exposure to harmful cosmic radiation. 2. Nuclear Electric Propulsion (NEP). NEP generates electricity through nuclear reactors to accelerate gaseous propellants. With projects like modular assembled radiators for nuclear electric propulsion vehicles, MARVL, NASA is working on modular systems that can be assembled in space. Such innovations promise to facilitate larger and more efficient propulsion systems, enhancing mission capabilities. 3. Artificial intelligence in space exploration. AI technologies are being integrated into navigation and system management, providing autonomous support for astronauts. These systems can handle routine maintenance and emergency scenarios, reducing cognitive load and improving mission reliability. Implications for human exploration of Mars. The convergence of NTP, NEP, and AI is set to redefine human exploration of Mars. Here are a few critical implications. Increased mission frequency. Shorter travel times will allow for more frequent missions to Mars, fostering a sustainable exploration strategy. Enhanced safety, reduced exposure to cosmic radiation and other long-term space hazards will improve astronaut health and safety. Global collaboration. The complexity and cost of Mars missions will necessitate international cooperation, paving the way for a new era of collaborative space exploration. Economic and societal impact. The advancements in propulsion technology are expected to catalyze growth in the space economy. As private companies and governmental agencies invest in these technologies, the aerospace sector could experience a surge in innovation, creating new markets for space tourism, resource mining, and other commercial endeavors. The push towards Mars may also reignite interest in STEM fields, inspiring future generations to pursue careers in science and engineering. Moreover, successful missions to Mars could foster a sense of global unity as nations work together toward shared goals beyond Earth. Timeline of events. 2025, significant progress in NTP and NEP technologies is reported, suggesting that human missions to Mars could be feasible within a decade. 2029, experts predict that advancements in propulsion technologies will reduce travel times to Mars by 25%, enhancing the feasibility of manned missions. Challenges and considerations. Despite the promising advancements, challenges remain. Safety concerns. The use of nuclear technology in space raises safety and environmental issues that must be addressed to ensure mission safety and public acceptance. Regulatory hurdles. Developing and deploying nuclear technologies involves navigating complex legal and regulatory landscapes. Public perception. Concerns surrounding nuclear energy may impact public support for missions utilizing NTP and NEP. Conclusion. The advancements in propulsion technology, particularly in nuclear thermal and electric systems, signify a pivotal shift in our approach to interplanetary travel. As these technologies mature, they promise not only to facilitate human exploration of Mars but also to inspire global collaboration and innovation in the aerospace sector. The dream of Mars missions is on the brink of becoming a reality, redefining humanity's role in the universe and potentially transforming our future on Earth.